Hi everyone. So today we're going to continue on and finish up 5.4. So now that we have a derivative of a vector value function of several variables, we're now ready to talk about our pretty much the last tangent formulas. Okay, so this will title the same thing. We're going to call this our tangent approximation formula. Tangent approximation formula. So this formula basically would work with any type of function regardless of whether it's real value or single or vector value, single variable or several variable. And this formula basically states the following. Let's say given a function f that map from Rn to Rm. And we're going to say, let's say vector y is equal to f of vector x. And of course, if m is 1, then instead of vector y, we just have y. If n is 1, then instead of vector x, we just have x. Okay? Then, the tangent approximation at x sub 0, vector x sub 0, is given by the formula. And we're going to call this tangent approximation t, just like what we used to do. T of vector x is equal to f of vector x sub 0 plus f prime of vector x sub 0 multiplied by x minus x sub 0. Now that formula looks strangely familiar to you probably because you probably remember me wrote a similar formula before, except that I just don't have all the arrows on top. That would be the tangent line approximation that we talk about, I would say probably in 5.2. So now that we have all the arrows on top, it just indicate now we have vectors. Now, however, important to understand is because in this case we have a vector value several variable function, we actually have matrix involved, and therefore it's important to pay attention to a lot of the dimension involved and how we write things. So here's how we look at this. So first thing I notice that f of x sub 0 is the output of the function f, which indicate that this is a vector in Rm. Okay? Both of these are x and x sub 0, which they are all input in the function. So therefore, these are vectors in Rn, which is different than vector in Rm, and therefore cannot be added together unless n and m are the same, which here we're probably going to say that they are not always the same. So then what happened here? Well, what happened is f prime. F prime is the derivative of a vector values function of several variables. Based on what we learned, this has to be a matrix. So this thing right here is actually the derivative matrix. And it has a specific dimension which is m by n. So now comes the important part. If I look at this as an m by n matrix, then I'm multiplying to a vector, and because of matrix multiplication is somewhat dimensions dependent, I have to represent this vector x minus x of 0 as a n by 1 matrix. And so now it makes sense because now these two things combine together. Notice that the n and the n are the same. That allow me to multiply them together and form an m by 1 product. And so our vector in Rm, which is f of x of 0, must also be an m by 1 vector for me to combine them together into a m by 1 sum. And that is a vector in Rm also, just written vertically. And so therefore this outcome must be the same, which is m by 1, a vector in Rm. Now, is that surprising that the tangent approximation is also m by 1 vector in Rm? No, not at all, because remember, one of the key features about tangent approximation is that it takes on the same exact type of function as f, as the function that is approximating. So in this case, I can conclude that t is also mapped from Rn to Rm. Very important, because of this matrix multiplication, you have to list the vector in Rn vertically so they can form the correct dimension matrix to multiply to the derivative matrix. And because of that, you also have to list the vector in Rm vertically so they can actually combine with the result of this product, which has a specific dimension matrix. So there are several things important to pay attention here. So let's go and talk about some of these important stuff. So number one, probably the most important thing about this tangent approximation is the following, which I already touched upon. If f mapped from Rn to Rm, then t also mapped from Rn to Rm. Okay, the tangent approximation has to stay kind of the same as the function f that it's formed from the tangent approximation from. And it cannot be something different, a different type of function. So what's the difference between the two? One of them, the difference is the following. This is an n-dimensional surface. Surface in Rm, and this is an n-plane in Rm. So they both have the same exact dimension because the dimension is defined by the domain of the function. They also exist in the same dimension because that's defined by the range of the function. The only difference is one of them is a surface which can have twists and turns and bent, while the other one is a flat plane. Okay, so that's the difference. That's the first difference between them. Two, in order for it to be proper tangent approximation, this must be true. F of x sub 0 must equal to t of x sub 0. And you can definitely see that is the case if you simply just plug into the formula. So show you. Here's my tangent approximation formula. And no dot product because matrix multiplication. And if I plug in x sub 0, then t of vector x sub 0 would equal to f of x sub 0 plus f prime at x sub 0. Oops. X sub 0 minus x sub 0. So guess what this come out to be? That come out to be the 0 vector. And guess what happened when you multiply 0 vector by a matrix? You get the 0 vector. And so that just come out to be 0 vector. And what do we know when you add a vector by the 0 vector? What do you get? Well, you get back whatever you started with. There you go. Okay, this must be true for tangent approximation. This statement, this must be true for t of vector x to be called a tangent approximation. And I'll explain a little bit more in a little bit as we go along. Don't worry, we get to explain. So why do I make such a big deal with all of this? Okay. Number 3. If m is equal to 1, that means we have a function that maps from Rn to R1, then t of vector x is an explicit function. Now, is that a surprise? Well, it shouldn't be. If m equal to 1, that means our original function f is mapped into R1. Therefore, it is an explicit function to begin with, and the tangent approximation just kind of inherit that property from f. Therefore, it's an explicit function. What if m is not equal to 1? In this case, I guess I probably should say m is greater than 1 instead. Then t of x is a parametric representation. And once again, it shouldn't be a surprise because if m is greater than 1, then the function f itself is a parametric representation. So therefore, t, the tangent approximation to it, also become a parametric representation. 4. So this is probably the most confusing part that you have to understand. The problem is that we have quite a few different tangent formula already. The problem is some of those tangent formula definitely create tangent, but there is a problem. The problem is the following. Okay, in 4.1, we learned this tangent line formula. Actually, I don't remember did I use vector t of t, but I think that's what the textbook used. Actually, I think I write this way. So this is the tangent line formula. I don't remember exactly if I use the same exact letters, but this is a tangent line formula. Okay, and in if I'm not mistaken, in 4.4, we learn a tangent plane formula, which I really have no idea what I label. Oh, you know what? Let me just look it up. Give me 1 second. So let me just look it up. So here's 4.1. Let's see what I use for the tangent line. Okay. Limits. Okay. Continuity, derivative, prime notation, blah, blah, blah. Okay. Tangent line. There you go. Oh, I did just use vector x. So I'm going to change that to just vector x. Let me do that before I forget. So here we go. And we're going to take this off. I think I mentioned that the textbook use vector t, but I avoid using it. So vector x is fine. So that's my tangent line formula in 4.1. And we can definitely look at the tangent plane formula in 4.3. So let's see what, oh, there you go. So I use vector x also. Okay. All right. All right, I'm going to just write that out. So I think I got it. Okay. So here's a tangent plane formula with vector x equal to t1 df over du at u sub 0 v sub 0, I think, plus t2 multiplied by df over dv at u sub 0 v sub 0 plus f of u sub 0 v sub 0. And this is my tangent plane formula. Now these two formulas are specific that I brought out. You also learn tangent line formula from BC Calculus. You also learn a different tangent plane formula in 5.2. But those two formulas are okay. The reason why those two are okay, because they're explicit formula. Okay, why are they explicit formula? Because both of those formula are for single real value function, which therefore they has to be explicit. And explicit functions are pretty unique. So why did I specifically pick out these two formulas? Because these two formulas, are parametric representation. And that's a problem. The reason why is it a problem? Because parametric representation is not unique. So therefore, meaning that these two things do represent tangent line, tangent plane, but they are not the only way to write the tangent line, tangent plane. And that becomes a problem. The problem here is that these two things, they do represent tangent line, tangent plane, but they do not represent tangent approximation. These two formulas are not tangent approximation. Now you might be asking, wait, why not? Why there's a distinction? Simply because the following. If you do plug in t sub 0 or x sub 0, u sub 0, v sub 0 into either of these two formulas, they do not give you this property right here. Okay? That's the problem. And so at this point, what I'm going to ask you to do is the following. Now, while you can certainly use these two things for tangent line, tangent plane, if the question asks for tangent approximations, these two formulas will not work. And they will not give you the correct answer. And therefore, I would totally suggest that at this point, you will pretty much forego these two formulas and learn to use this formula to replace them. Okay, so keep that in mind. These two formulas from 4.1 and 4.4, they do give you tangent line, tangent plane in a parametric representation, but they do not give you a tangent approximation. They only give you a geometrical interpretation of tangent line and tangent plane. And therefore, I would recommend that you don't use these two formulas from this point on, unless you are looking for just tangent line, tangent plane. But if the question asks you for tangent approximation, these two formulas no longer apply. Okay, so keep that in mind. Now, what I want to do is show you some example, and that would be it. That is the last thing I want to show you. That would be for tangent approximation. So show you some example and how to use the formula correctly. So let's say I'm going to give you this function. Let's say given f of t is equal to t minus 1 and t squared minus 3t plus 2. Okay? For, let's say, negative infinity to positive infinity for t. And I'm going to go ahead and ask you to find the tangent approximation for f of t at, let's say, t equal to 2. And so this will probably be a good example to illustrate why it doesn't work. So show you the following. So here, probably the most important part is that the question asks for tangent approximation. Therefore, if you use this formula, you will get a tangent line. This formula is not like fake. It is a real formula that will give you a tangent line. The only problem is that it will not give you a tangent approximation. So I'm going to show you why. So how about we do that first, and then I'll show you how to use the tangent approximation formula that I presented to you in this section. So let's say I'm going to try to use this tangent line formula. So the tangent line formula basically says this. So it shouldn't be too hard to figure this out. So let's do this. F of 2. So what is f of 2 equal to? Well, that will be 2 minus 1. 2 squared minus 3 times 2 plus 2. So 2 minus 1 is 1. And then that's 4 minus 6 is negative 2 plus 2 is 0. So that's pretty good. So f of 2 is 1, 0. Let's do f prime. F prime of t would equal to 1, 2t minus 3. So f prime of 2 would equal to 1. 1. So I can definitely use this formula for tangent line. There you go. So that would be a tangent line formula. So important to note that this is a tangent line. But not tangent approximation. And so you're probably still thinking, like, why not? So here's why not. Remember, one of the most important property about tangent approximation is that this must be true. F of x sub 0 vector x 0 must equal t of vector x sub 0. Meaning that if you plug in the point where you're forming the tangent approximation into the function f, and also into your tangent approximation, they should always give you the same result. And if they don't give you the same result, what you have is not a tangent approximation. So therefore, implying that if I put my t equal to 2 into this formula, I should get the same thing as f of 2. So let's see what happened here. So I'm going to go and call this t of t, I guess. That's my tangent approximation. Okay, or claim to be tangent approximation. So notice what happened if I plug in 2. Notice that t of 2 does not equal to f of 2. That's the problem. That's why it is not a tangent approximation. And some of you probably already noticed the reason why. The reason why is because of this perimeter. Notice that in our tangent formula, we have this subtraction involved that scale our tangent approximation to the right spot, which is x sub 0. This does not have that. Okay, as a matter of fact, if you look at these two formula, neither of these two formula has that little minus part on our input. While the other two formulas, the one that you learn in BC calculus for tangent line and the one you learn for tangent plane in 5.2, both have that subtraction involved. And that's the reason why neither of those two are an issue. They're both tangent line, tangent plane formula, as well as tangent approximation formula. These two formula on screen, 4.1 from 4.1 and 4.4, they are not tangent approximation formula because they are simplified to take advantage of the fact that they are parametric. Therefore, we don't really need to care too much about the specific of it because you can have multiple representation that will still work. So these two would definitely form tangent line, tangent plane, just won't be tangent approximation. So now show you how to use our tangent approximation formula. So to use the tangent approximation formula correctly, you just really have to pay attention to a lot of the dimensions so that you don't screw up your problem. So here's our function, f of t equal to t minus 1, t squared minus 3t plus 2. So if I look at this correctly, f go from r to r2. Okay? Now I'm going to use my tangent approximation formula. So here's my formula. So first thing I'm going to do is I'm going to rewrite it based on what this problem is. So this problem, the input is just t, not f vector x. So I'm going to rewrite that into this. So this formula basically turns into this one. Capital T of t equal to f of t sub 0 plus f prime at t sub 0, t minus t sub 0. Now let's pay attention to the following things, okay? F of t sub 0 is the output of the function f. That means this is a vector in R2, which I have to list it at 2 by 1. This is T minus T, so it's a complete scalar. I can think of scalar as 1 by 1 matrix. What happened to F prime? F prime, in this case, I'm going to represent it more or less like a derivative matrix. And in this case, the dimension of the derivative matrix would be M by N, which is 2 by 1. Notice if I multiply 2 by 1 by 1 by 1, I do get 2 by 1 matrix, which can allow me to add to a 2 by 1 matrix to give me a matrix, to give me technically a vector in R2, which is exactly what capital T should give me, because capital T should give me the same thing as F. So now I'm ready to actually do the problem. So what is T of T equal to? So we already know what F of T sub 0 is. That would be T sub 0 would be in this case. Oops. Maybe I'll write out extra step. At t equal to 2. So therefore f of t would equal to f of 2 plus f prime at 2, t minus 2. Notice that t, okay, maybe I should write this as t sub 0 equal to 2. Okay, because technically it's t equal to t sub 0, and so since this is t equal to 2, 2 and t sub 0 are the same, but if you get confused, you can say at t sub 0 equal to 2 if you want. So therefore that would mean that t of t would equal to f of 2, which we already know that is 1, 0. And no, you cannot write this horizontally. You have to write it vertically as 1, 0, one on top of each other. Plus f prime of t would be, f prime of 2 would be 1, 1. And yes, you have to write it vertically also in this case because it has to be a 2 by 1 derivative matrix. Multiplied by t minus 2. So what does that turn into? It turns into, it turned to 1, 0 plus t minus 2 times 1, 1. So therefore just become t minus 2, t minus 2. And so from this, I would say that this is equal to t minus 1, t minus 2. Or if you prefer, you can think of it as this, t times 1, 1 plus negative 1, negative 2. Now, I'm claiming this is my answer, okay? Either way to write it is fine, unless the question dictates otherwise. Let's look at what happened if I plug in 2. So that would become 2 minus 1, 2 minus 2, and voila. That is exactly what f of 2 is equal to. This is now a tangent approximation. Now, then some of you might ask, well, is this still a tangent line? Yes, it is still also a tangent line. Meaning this formula provides us with both a tangent approximation as well as a tangent line, which is why it's superior than these two formulas that you learn in 4.1 and 4.2, that they only provide tangent line or tangent plane, but not tangent approximation. But any tangent approximation that you find will also serve as a tangent line or tangent plane or tangent hyperplane or tangent end plane, whatever it is. All right. Now, maybe I have time to do one more example. So let me do one more example. How about let's do one that's really have to use this formula because technically speaking, you can use the formula that you learn in the explicit one, meaning the one from BC Calculus as well as the one from 5.2 for those specific type of function. Okay. But let's do this one. Let's say we're going to give an f of uv is equal to u cosine v, u sine v, v. So this is basically the helix that we have. And I'm going to go ahead and ask you to find the tangent approximation. At, let's say, 1 comma pi. So how do we go about doing this? The same way. I'm going to go and first define that f, in this case, must be from R2 to R3, because they take two variables, u and v, to define, and they pop out 3 different coordinate functions, so therefore it has to be in R3. So therefore, if I now look at my tangent approximation formula, t of vector x equal to f of vector x sub 0 plus f prime of vector x sub 0 multiplied by x, vector x minus vector x sub 0 will now become the following. It will be t of uv equal to f of u sub 0 v sub 0 plus f prime at u sub 0 v sub 0 multiplied by uv, which is what vector x would be in this case, minus u sub 0 v sub 0. And what is u sub 0 v sub 0? U sub 0 v sub 0 in this case would be equal to 1 pi. So therefore, okay, let me see. Okay, let's move it this way. There you go. Then therefore our tangent approximation formula become t of uv equal to f of 1 pi plus f prime at 1 pi multiplied by uv minus 1 pi. So now let's try to find what we need to plug in. So let's start with f of 1 pi. F of 1 pi would equal to 1 cosine pi, 1 sine pi, pi. So what's that equal to? So cosine pi will actually be -1, sine pi will actually be 0, and then pi obviously is pi. I do need the derivative matrix. So in this case, if you think about it, once again, think about dimensions here. F is the output of function, so therefore has to be a 3×1 matrix. F prime would have to be a 3×2 matrix. Remember, it's m by n. And what is this uv minus 1 pi? Would have to be a vector. So I'm going to have to write this vertically in order for it to work, which I'm going to do that in my next step once I'm ready to do it. But it has to be a 2×1, otherwise I will not be able to multiply. Okay, so let's go and find f prime and then we can evaluate. So f prime of uv would equal to, so hopefully by now you're pretty good at take the derivative to find the derivative matrix. So first I'm going to differentiate with respect to u, so therefore it's cosine v. And then take the derivative of v, that would be -u sine v. And then sine v, u cosine v. 0, 1. And so if I put in f prime at 1 pi, what I have will be the following. I will be cosine pi, which is -1. -1 sine pi will be 0. Sine pi will be 0. And then 1 cosine v will be -1, 0, 1. Okay, so now I'm ready to actually go and do my formula. So I'm going to continue my formula down here. So therefore my tangent approximation formula will be T of uv, which is equal to -1, 0 pi plus -1, 0, 0, 0, -1, 1 multiplied by u minus 1 v minus pi. And you have to write it this way so they can multiply properly. So now I'm ready to form my tangent approximation. That will be -1, 0 pi plus, so that times that would be negative u plus 1. This time this would be -v plus pi. This time this would be v minus pi. So if I'm looking at this correctly, this T of uv would equal to -u plus 0, because -1 plus 1 is 0, -v plus pi, and then the pi cancel here, so just be v. You could write it out this way by just organizing the vector. And give me 1 second. Move over here. Good. And then plus, so that would be my solution. And you can verify what happened when you plug in 1 pi, and you should get -1, 0 pi as your solution. All right, so that's the end of 5.4. So I'll talk to you again in the next video. All right, bye bye.